point Z. Okay, I try to construct as accurately as possible. So I'm just going to construct the negative. So minus 180, 160. Maybe I don't need 160. Maybe I can go up to 160 only. Minus 160, 140, 120, 100, 80, 60, 40, 20, 0. So everything is minus. Shear clockwise, anti-clockwise. Minus 20, minus 40, minus 60. Probably I need minus 80, but don't worry. 20, 40, 60, 80. Okay. So my 3 points that I know, or we know that this is our point Z, right? And then we have our minus 130, different color. And then we have our minus 70. Then we have our 40. And then we have the other 40. By the way, I posted the homework already, okay? So this is my point X at minus 70 line, right? It's going anti-clockwise. So this is my point X. And over here, this is my point Y, okay? So from here, I'm eyeballing this, okay? So the center of the circle is still here, right? There is your O, right? So to get the radius 20, 20, 30, so 40. So 40 squared plus by 30 squared, the square root is equal to 50. So this circle is 50. So 50 radius, so 50, so 20, so will be here. And then 50 will be there. So this is my circle. Hey, wait. 20, 40, 50 should be here. Okay, so this is 50. And this is 50. So this is circle number 1. So this is for XY plane. Then I can construct the other circle. 50, so 25. So this will be my XZ plane. And then the bigger circle will be, I think it will be 75. Yeah, it will be 75 because it's exactly the same. Moose, make sense or no?
Yep, got it.
You cheeky sock.
Perfect, thank you. I just wasn't sure. Okay, yeah, that makes a lot of sense. No, thank you.
What do you mean you're not sure? You just make me do reverse. Okay. Everyone, are you okay with that? I think it's a good example to show, like, if you are given this, how to draw 3D Mohs circle. There you go. Okay. So the final one, this is your YZ plane.
Eugene?
Yes.
Sir, you know how you said X is counterclockwise and you drew it at the bottom? Why is it like that? Like you said something about counterclockwise.
So this one, okay, look at X point.
Yeah.
You look at this one, the rotation is anti-clockwise. So anti-clockwise.
Oh yeah, no.
Oh yeah, Vidu-san, sleeping Vidu-san.
Sorry, I forgot. Thank you.
Okay, so now the final one, okay? It is Tresca-U criteria. Okay, Tresca-U criteria. Vidu-san. I'm gonna miss Vidu-san. No, I'm gonna miss all of you, man. And some of you say, yeah, Eugene, we don't miss you, okay? Tresca. So I don't know, did I explain why I spell Tresca that way, right? I use tau, right? You can see that over here, I use a symbol like tau, is because Tresca is based on maximum shear stress criteria. Okay, it's based on maximum shear stress criteria. Okay, so if you are given the yield strength, okay, if you are given the yield strength, okay, the normal yield strength, the shear, okay, so stress yield is given, right? So the shear, right, the shear, so based on Tresca criteria, right, the maximum shearing stress is equal to the yield divided by 2. That's it. Okay, the yield divided by 2. Okay, so this is usually applied for ductile material. Okay, usually applied for ductile material. Right, so this is what Tresca mean. Okay, so what I'm going to do next, I see how much space I have, quite a bit. I'm going to do one problem, okay, that use the maximum shearing stress criteria. Okay, again I say I'm going to do one problem that use the maximum shearing stress criteria. Okay, so this is our example number 2, and you have seen this example before. Okay, and this is like I will show you the example. Okay, I'm going to copy. Okay, so this is the example that we are going to do. Have you all seen this example before? Anyone?
Is this from 3CO3?
Vidusan, you are sleeping today, you know, Vidusan. It's not.
Oh shoot, okay, I'm gonna just stop talking about.
Yeah, have you seen this before? Anyone? So if I go back long enough, week 1, before I have Bell's Patsy, okay, right? This is the exact example that I show you guys on the very first day, okay? The exact example, okay? Right? The exact example. And now, so we went through, I was trying to inspire you guys, okay? Why this is critical, how to calculate this, okay? And then we started to do some analysis, right? Not a lot, we did not put numbers in, okay? So what I'm going to do now, okay? So you guys see down here, hey, we see elements, yes or no? So some of you ask me, Eugene, how do you construct the elements, right? You guys ask that, right? How do we construct elements, and which is the biggest space, which is in plane and which is out plane? Unconsciously, you guys know, seen it before, okay? So now I'm going to go full circle, okay? So this is how we're going to end our course, okay? We're going to end with a full circle, right? So what we have, this is a shaft, okay, a drive shaft. So the torque is at 2000. So now when we look at torque, like, yeah, Eugene, we know this, okay, 2300. And then we have a moment 1500, right? And then we have a thrust of 2500. So given that the yield, now you understand what all these values are about now. Hey, I know what is this now, right? Given that the yield is 100 KSI, okay, and the shear is 50. It happened to be this problem is very gentle. Okay, what do I mean by gentle? They will give you that the yield, the normal stress in yield is 100, and the shearing stress in yield is 50. It is possible that these numbers are not half, but again, I say this is a question that they are very gentle with us. Okay, so they want us to determine the shaft, diameter of the shaft, using the what? Maximum shearing stress criteria. Okay, so this is given. Okay, this is given maximum shear. So now we know, like how I taught you guys to remember, right? That when we are given maximum or maximum, they call it maximum shear stress criteria, right? So we know that this is equal to what? Tresca, right? Shear. Okay, so this is equal to Tresca criteria. Now, usually in problem sets, okay, they don't say maximum shear stress. Oh, when you go to industry, they expect you to know what is Tresca, what is von Mises, and what is Mohs criteria. Okay, the expectation. Now, for this course, I had supposed to cover all three, but due to shortage of time, I only can cover what? Tresca. Okay, only can cover Tresca. Right? So Dr. Jane, the next course you're going to take 305, I already told him that what I have not taught, he will go through the other criteria also. Okay. So this is Tresca criteria. So we know that for Tresca criteria, it's usually used for ductile material. Right? And we know that the yield is equal to normal stress yield divided by 2. Okay. So for this case, it happened to be the same. Okay. It happened to be the same that we are given that the stress yield is equal to 100 times 10 to the power 3 psi. Now, some problem sets were not, or some, if you go to industry, there's a possibility that this value is not given at all. Okay, so you have to calculate, yes or no, using what? Using Tresca. You have to calculate. So if that value is not given, you're only given that normal stress yield is equal to 100. You have to calculate it based on Tresca, and you know that the shear yield is equal to 100 times 10 to the power 3 divided by 2. So this is 50 times 10 to the power 3 psi. Okay. And usually, if you look at any handbook, okay, the most values that are given is in what? Tension or what? Compression. Okay. Very seldom they show you data in terms of shear. Okay. So if you don't know the value in shear, you can say you use Tresca criteria and you calculate it to be equal to 50 times 10 to the power 3. Are we clear? Any questions so far? Okay. No. Right. So now we know that this is a 3D problem. So we're going to label this as X. Okay, X. Over here is your Y. And then this direction is now Z. So now when you see me doing this example, you'll be very familiar. Could you remember the very first day when you saw me doing this? All of you say, holy shit, yes or no? Right? But now it is so familiar to all of you now. It's no big deal. Can someone tell me, am I right or wrong? Anyone?
You're right, sir. You're right.
Right? You see, you're like, whoa, this is so easy now, right? Right. So from here, right, based on how we label, so we know that stress X. In fact, you guys can do more complex problem now. Okay, this is Mickey Mouse to all of you. Okay, so PX. I can even make the shaft thick and thin wall. You guys can even handle it. Okay. Right. Then we know that torque. The X. By the way, the question is in the what? In the Avenue to Learn. Okay, you can download and see. Okay, so this is 2,300 pound-feet. Okay, I'm going to immediately change to pound-inch. Why I have to change to pound-inch? Because this is in inches. Okay, so 2,300 feet to inches is just multiplied by 12. So this will get us 27,600 pound-inch. Okay, and then moment in Z is given to us to be 1,500 pound-feet. So this is equal to 1,500 multiplied by 12, right? So 1,500 So it's equal to 18,000 pound inch.